If you've ever studied a simple harmonic motion, you've probably come across these formulas. X is equal to a sine omega t plus delta, and the velocity v is equal to a omega cosine of omega t plus delta. But how do you actually get these formulas? Let's take a look at a very base example. So let's say we're starting over here. O over here is the origin, but you're not starting over there. You're starting as a particle at some position x sub 0, right? So x naught. You're going with a velocity v naught. And what's happening here now is that because you're undergoing simple harmonic motion, there is going to be a velocity, there's going to be a force that you're experiencing. And the particles, this is the particle over here, just to be clear. The force that the particle is experiencing is going to be negative k of x. But typically in simple harmonic motion, you would write this as negative omega squared x, right? This would be the acceleration. So the force, so this is the acceleration, so this would be times m. This would essentially give you the force, right? Because this is the acceleration times the mass, that's the force. And again, yeah, I should also mention this has mass m. Okay, so that's how we're setting it up. We know that these two things are equal. We know that the x is in common. So, and there's a negative in front as well. So this tells us k is equal to omega squared m. So omega squared is equal to k over m, which means omega equals the square root of k over m. So that's the first thing that we're going to do. Just keep that aside, and we might come back to that later, but this is the way we're going to write it. Now, if we know that the force is equal to this, we're kind of working backwards here, but we knew that the acceleration is equal to negative omega squared x, right? How can we move on from here, right? We are nowhere near these formulas that we have over here. One hint might be, well, we've got an x over here, right? If you want to integrate, if you want to do anything, we want to get it in terms of x. And what is acceleration? Acceleration is dv dt, right? But what is, so it's a derivative of velocity, but what is dv dt? We can also write that as dv dx times dx dt, right? And so dx dt, this is the velocity. So we can write that as dv dx times v is equal to negative omega squared x. Now we can multiply both sides by dx. And so what we're going to get is v dv is equal to negative omega squared x dx. We now integrate both sides. One second, just like that. And in doing so, we get v squared over 2 plus c, right? But we don't need to write that yet. You'll see why. Is equal to negative omega squared x squared over 2 plus c. But let's not actually do the plus c's right now, because there are certain bounds that we're going to be using. And the bounds that we're going to be using are from x in general and v, whatever the v is going to be. And then, sorry, I think my network went out for a second. So over here, we're going to go from v sub 0 to v. And over here, we're going to go from x sub 0 to x. Okay, and in doing this, what are we going to get? On the left hand side, we're going to get v squared over 2 minus v naught squared over 2. On the right hand side, we're going to get negative omega squared. Then over here, we have x squared over 2 minus x naught squared over 2. First, we can multiply everything through by 2. I'm going to move my camera up to the top left, so it's kind of out of the way. Once we do this, we are going to have, so we can multiply everything through by 2. And we get v squared minus v naught squared is equal to negative omega squared x squared minus x naught squared. How can we proceed from here? Well, we can now isolate v squared. So I'm going to continue up here, right here. We want to isolate v squared and see what we can do from there, right? So we just add v naught squared to both sides. That gives us v squared is equal to v naught squared. And then on the right hand side over here, we actually write this as plus x naught squared omega squared, and then minus omega squared x squared. So what is v going to be? V is just going to be the square root of this entire thing right here. Okay, let me write this a little bigger. We can actually take out, so we need to be a little bit careful with how we do things here, but essentially we can take out an omega squared. We're taking the square root, so that's going to mean just taking out an omega. Inside here, what do we have? We have v naught squared over omega squared, right? We can't forget that. And then we have plus x naught squared minus x squared. Okay. Yeah, I want to scroll down so we can make some more space. And I'll stick with the same colors though. I might change them later on if it's getting a little too messy. Let's continue now. Right here. Okay, so where were we now? It looks a little bit messy, so we don't want to necessarily continue the way we are right now. So let's make a quick little substitution. Um, let's call that a squared. So a squared is equal to v naught squared over omega squared plus x naught squared. And so now that we're done with this will simplify it nicely. We have v is equal to omega times the square root of a squared minus x squared. Keep in mind now, right? So we change omega. So if you look above over here, omega is the square root of k over m. Over here, a squared is equal to v naught squared over omega squared plus x naught squared. So there are definitely some simplifications that we made here, but the important thing to note is that a squared is independent of x, right? It's dependent on these other constants, v naught, x naught, and omega, as you can see here, it's k over the square root of k over m. So all of that is independent of x. So it's not like we're just abstracting a variable away to a constant, right? We're still keeping the variables as they should be. Now all we need to do is simplify this, and the way to do that would be to again go back to the definition. What is v? It's just dx dt. So the left hand side, we're going to have dx dt is equal to this. So there's omega right here. And then we have the square root of a squared minus x squared. Pause the video, see if you know how to work it from here. All we're going to do is divide both sides by the square root of a squared minus x squared and multiply both sides by dt. So it's like a differential equation, but not a very difficult one, right? If you've taken calculus BC, this is one of the types of differential equations that you will have learned how to solve. So all we have now is this, right? It's a separable differential equation, so it's not super difficult at all. Omega is independent, or it's like a constant with respect to time. This one, if you recognize this, that'll make things a lot easier. Otherwise, you might have to use trigonometric substitution. But regardless of whatever method you end up using, you're not going to have a lot of trouble with this integration, hopefully. So I'm going to integrate it. By the way, just remember, when I did this integration here, I was a little pressed for space and time, so I didn't put the bounds, but there, of course, there were bounds. It is v naught to v, x naught to x, right? And we'll have a similar situation over here. T is going from 0 to t, and then because that's how we defined it, right? That's how we initialize everything. T equals 0, x naught, v naught, etc. Let's integrate both sides now. A squared minus x squared is equal to the integral of omega dt. What is the, so let's do the left hand side first. Actually, let's just do this. X naught and x, this will be 0 and t. Right, we're putting these bounds based on what we're integrating with respect to. Over here it's x, so that starts at x sub 0, goes until x. On the right hand side, it will be with respect to time, which starts at 0 and goes until t. Okay, what do we get? The left hand side is, I believe it's inverse sine of x over a, and it's going from x naught to x. Over here we just have omega t from 0 to t. Okay, let's continue. Let's see what we get now. So over here we're going to get this. Okay, is equal to well, what's that? That's just omega t, right? And so that's not super difficult. Now we make a third substitution. We're going to, okay, let's actually just do the next step. Pretty logical step, right? Is equal to, now important to note here, this is x. There's how many x's are there over here? There is only this one x, and we're going to solve for that x now. So it'll be a little bit difficult, but we're going to find that. This x naught is not, pun intended, this is not like x, right? Keep that in mind, because otherwise, first of all, obviously that just becomes 0, because it's like this one thing minus the same thing. But you can call it a variable because x naught is a constant, right? That's just an arbitrary position at which you start. Anyhow, we have this omega t plus arc sine of x naught over a. Here, this one you can probably recognize. Actually, if you go all the way back up to the form, you can probably guess where I'm going with this. But you're going to let arc sine of x naught over a, we're going to just let that equal delta. So now we have sine inverse of x over a is equal to omega t plus delta. We take the sine of both sides. We get x over a is equal to sine of omega t plus delta. Okay, what's the last step? We just want to solve for x, so we multiply both sides by a. And in the process of this, I accidentally made a lowercase, which obviously that's a completely different thing. It should have been uppercase here, should have been uppercase here, and here, and here, and in all these other places. So just forgive that mistake, please. Where else here? Okay, so x is now equal to a sine of omega t plus delta. It's a long process, but we're finally back to what we wanted. Right now, how can you find v? You can probably guess this. We've done a lot of integrations. Now we do the opposite. We do a little differentiation. We differentiate both sides with respect to t. So dx dt, that's nothing but v. On the right hand side, we use the chain rule. So there's going to be an a. What's the derivative of this inner thing? It's just w, right, with respect to time. And then what's the derivative of this with respect to this? It's just cosine of the inner function. Okay, and just say that we're done with this one. And of course, we already did the previous one right here. So with that, we have proven the two big equations for simple harmonic motion. I know there's a lot. I'm going to scroll up very quickly. You can look over any areas that might have been a little troublesome or that you might not have thought of. So yeah, that definitely was out of algebra, but hopefully none of it was too difficult. And of course, I showed a lot of steps. A lot of these are very straightforward steps. Like I hope you could have gone from here to here and here by yourself, right? But I just wanted to be thorough in the way I'm doing it. So I hope you enjoyed this video. I hope you learned something new, and let me know if you have any suggestions for a future video. Thanks so much for watching.